Hi everyone, my name is Hadi Nabi Muhammad Ruzlan. My metric number is B0821110053. I will present about introduction of optical network system design and performance analysis considering variable photodetector and laser wavelet. The research depth into the foundational aspect of optical network design considering architectural choice, technological components such as laser and photodetector, and the challenge associated with dynamic wavelength variation. The investigation emphasized the critical role of photodetectors and laser in optical network and their impact on signal transmission reliability and overall efficiency. A comprehensive performance analysis is conducted, quantifying losses induced by variable wavelength sensitivity assessment evaluate the repercussion on crucial parameters like bit error rate and signal to noise ratio. Why? Practical experiment validate theoretical models, ensuring the relevance of findings. The study recognized the dynamic nature of optical network, addressing considerations such as wavelength division multiplexing, integration, and the influence of environmental factors. Ultimately, the outcome of the research contribute to the evolving landscape of optical communication. They offer a nuanced understanding of how change in photodetector and laser wavelength impact system design and performance. As optical network evolve to meet growing demands, the study serve as a guide for the development of adaptive and robust communication infrastructure capable of effectively navigating challenge associated with dynamic wavelength scenario. That's all for me. Thank you.
Hi everyone, my name is Ganesh son of Raman. My metric number is B08211051. Today I'm going to present about the methodology of a characterization of optical system. So we use Optic system software, which is version 7.0, and then we build the circuit. So this is the circuit we built. So I want to explain about the components. So the component we use is P0 random bit sequence, NRZ, pass generator, max generator, modulator, CW laser. These are the four components very important to build an optical system circuit. Not only for this circuit, but other type of circuit also is very important because this will transmit the power fiber signal. Then from max generator we connect to the optic fiber. The optic fiber then we set 10 km. For us is 10 km, but we can set to 100 km, 200 km, 300 km, depending on the user. Because the fiber optic, means the optical fiber will transmit the signal to longer distance. And then optic attenuator means they reduce the power or attenuating the power. So the attenuation we set is 5 dB. Then we put the power splitter to split the circuit because we're using a photodetector PIN and a photodetector APD to observe the losses, power receiver, the eye diagram. Both are for both photodetector. Want to compare which is called high losses or which is called a minimum power receiver. Want to compare which is good. Want to compare. That's why we make it two powers. Make it split the circuit. So we use the optical amplifier, optical fiber, optical attenuator, then photodetector PIN, low pass basal filter. So these four components we use for the photodetector APD. Same concept. Then we use the VR analyzer to observe the eye diagram and QR factor, Q factor, and optical power meter to measure the power receiver or the power losses. So then we run the circuit. Then we get the value like this. This is the output we get. So this is called the eye diagram. It's looking like eye, so we call eye diagram. Then because the signal, if you look, the eye diagram is very small and perfect. So this which means the signal is good. Then the application of the optical system is fiber to the home. The fiber to the home definition is connect the optical fiber directly to residents, apartment buildings, and businesses. Most of fiber to the home mostly used at the all last mile telecommunication. Optical fiber can transmit data by using light signal to achieve higher performance. The main benefit of the fiber to the home is increase the network performance, and it can provide the higher speed over longer distance with the higher bandwidth. If you compare to the coaxial cable, distant cable, this cannot bridge because it only provide to shorter distance. But use the fiber to the home, it can provide high speed with a longer distance, and also provide a better bandwidth. The photodetector we use is avalanche photodetector and PIN photodetector. The avalanche photodetector is mostly used in the laser-based fiber optic system to convert the optical data into the electrical form, which is very sensitive compared with the PIN photodiode. The PIN photodiode is very common used in the optical fiber communication. So in the PIN, we call the PN region. It means we call in-strip thin region. They got positive region and negative region. So inside that, the most photons are absorbed in the in-strip region, and the carrier produced there will make an effective contribution to the photopharon. In design parameter, we set the wavelength for CW laser at 1310 nanometer and 1550 nanometer respectively. That is the parameter we included in the insert in the components. The performance of parameter regarding to the losses and quality of signal by varying the type of photodetector. The component we use is P0 and the bit designed using the RT and serially interconnected deep flip-flop based on two couple polarization switches, and NRZ pulse generator, which called non-return to zero, can coordinate electrical signal which is dependent on the bit sequence input. CW laser is continuous wave fiber laser, converts the input pump power with a low coherence to a highly coherent optical output signal, which is constant in amplitude and wavelength. Next is max generator modulator used for controlling and used for controlling the amplitude of an optical wave. Optical fiber and optic attenuator power split the positive the APD, positive the PIN, that's why I was explaining. So the low pass band filter used in the application where a constant group delay is like which is critical. We are analyzing to observe the Q factor and I diagram. Optic amplifier amplify the light as initial without converting the optical signal to the electrical signal. Optical power meter to measure the power receiver or power nozzle in the optical signal transmitted to the fiber. Other than that, the drawback of the optical system is the advantage of the optical system is it can provide a longer distance, can transmit to longer distance with a better or higher bandwidth, and the disadvantage is the cable is fragile, it's easily can broken because inside the core is made by the glass. Once the cable is broken, remains is very the system is failure, the fiber will fail to transmit, need to redo again. And then the fiber optic cable is very expensive compared to the coaxial cable or other type of cable. So that's it.
Hi guys, my name is Chang Chun-hen and my metric number is B0821101140. So I believe that my teammate Ganesh has explained to you guys about how we constructed the circuit and the components of it. So right now I'm going to discuss about the result and some discussion. So basically we use the 1:2 power splitter to connect both photo detector, which are the photo detector PIN and the photo detector APD, and then by using the two different values of the wavelength, which are the 1550 nanometer and the 1310 nanometer, we can observe. So for the first one, is the laser wavelength of 1550 nanometer. So as you can see, we use the fiber length with 30 km, and then these are all the outputs that we get. So from here, the main factor that we want to observe is the Q factor. And here you can see that the APD is around 8.86, and then for the PIN is about 4.56. And then you can take a look at the eye diagram. So this is for the PIN photo detector. This is for the APD photo detector. Next, we change the wavelength to 1310 nanometer, and then we observe again the value of it. Same things, we need to look at the Q factor here. As you can see, the photo detector APD, the max Q factor is higher than the photo detector PIN. And then these are the eye diagram for the PIN photo detector, and then this is for the APD photo detector. And then from here, we can realize that overall the max Q factor of the 1310 nanometer is slightly higher than the 1550 nanometer. And then we can observe that the eye diagram of the APD photo detector is sharper compared to the PIN photo detector. This is because the increased degree of sensitivity of the APD generated by the avalanche rise. So in conclusion, we think that the photo detector APD performs better than photo detector PIN because of the higher max Q factor. Because the higher max Q factor, the better the signal is. Once we finish the observation, we realize that there is some improvement can be made. Therefore, we add the two gain amplifier with 20 dB in front of the photo detector, and then you observe again the eye diagram. As you can see, this is for the PIN photo detector, and this is for the APD photo detector. Compare these two with the previous eye diagram, you can see that the eye diagram is become much sharper and clearer. And then this is all the value that we observe. Same things, we can take a look at the Q factor here. You can see that both photo detectors has increased to 18 point something, which secure a better signal. So when compared to previous study, it's the improvement in fiber losses based on the modification that we made, and for the both photo detectors, the reduction is the negative 31.649 dBm, and another one is the negative 22.106 dBm respectively. This is because the APD increased the sensitivity. So when we're comparing to the previous study, the eye diagram using the photo detector PIN will show some significantly improved result in terms of reduced distortion, increased signal to noise ratio, and also enhanced the clarity. It is because the optical amplifier in the channel has enhanced the signal that was transmitted by the transmitter by 20 dB of gain. So that's all from me today, and thank you very much.
In conclusion, the characterization of optical networks through the design and performance analysis has provided valuable insights into the intricacies of the systems, particularly in terms of losses attributed to varying laser wavelength and photodetector configurations. The comprehensive exploration of these parameters has not only enhanced our understanding of the optical network's behavior, but has also paved the way for optimizing system performance. As technology continues to advance, the findings from this characterization will serve as a foundational resource for future developments in optical network design. The optimization of laser wavelength and photodetector configurations will play a pivotal role in addressing the ever-growing demand for high-speed, low-loss communication networks. The knowledge gained through this research contributes not only to the theoretical understanding of optical networks, but also holds practical implications for the implementation and enhancement of real-world optical communication systems.